All right, let's have a look. 5i exponential growth. I don't know why I copied that actually. That's it should have been growth and decay. General exponential equation for modeling is this one. Okay, so we usually use base E, but it really depends on the question. So if the question normally says like doubling, then that's a hint that it's going to be base 2, tripling, base 3, halving, base half. Okay, so what I'm talking about is this right here. So it's not always E. That's Euler's number. If they wanted to use E, they would tell you. Okay, so depending on the question, you have to then think about that. What's A naught? Well, that is the dilation factor, and often that is the starting amount, its initial amount. So here they say A naught is the amount that you initially start off with, okay, and then it grows or it decays by a certain amount. So you can think of like back in year 9 and 10, you would have learnt the formula for compound interest out of interest. Does anyone remember what the compound interest formula is? The general class would do this to death, but what about the methods team? What's the formula again to find compound interest? So if you're borrowing money from a bank, you borrow, I don't know, say $1 million, and you're going to borrow for the next 30 years, and the interest rate currently is about 6.05. Over 30 years, how much will you end up paying in terms of interest? There's a formula that you can use to calculate it, assuming the interest rate does never change. Anyone remember? Hands up.
I'm going to give it a go.
Yep.
It's the principal amount times by 1 plus the rate over 100 to the power of n, where n is the years.
My pen died. I think you killed it with too much maths, Pat. Give me a second. What's going on? Ooh. That's no good. Let's refresh a bit. See if I can put in, and it should be recording now. Yes, it is. All right. Sorry, Pat. Bit of a tech issue there. Principal times.
In brackets, 1 plus the rate in percentage over 100.
Rate in percentage, so out of 100.
To the power of n, where n is the time. It's usually years, but sometimes it can be months or every quarter or every...
Very good. That is correct. This is the formula for the compound interest. So P, which is how much you borrow. So if you borrowed 1 mil, okay, and 1 is pretty much 100% of itself. The reason why there's the plus percentage is the interest rate. So you pay 100% of itself. So if I borrowed mil, then if it was just 1 to the power of anything is just 1. So you always pay back what you borrow, right? But that's not how the bank works. The bank normally says, well, I'll give you the money, but over time you're going to pay me a little bit extra out of nowhere, right? So that little bit extra is where the rate comes in. And then obviously we haven't talked about how often they compound this, meaning how often do they charge you interest? Is it after every single day? Is it after every single hour? Is it every week, every month? This here is just to summarize how many years you want, but it doesn't tell you how many times they do it. So usually N is the number of years that you've got to borrow it for. So usually a home loan is about 30 years. You'll learn all this if you do general, and those who do general might know this quite familiar. 30 years, you borrow for 30 years. The interest rate is over here. So depending on your interest rate, that's your interest rate. And how many times they compound? Normally they compound every day. So for the amount of money that you have every day that you put money into the loan that you owe, that reduces the interest rate every single day. But the repayment is always calculated by monthly. So by the end of a month, they would have calculated interest every single day up until a month, and you pay a certain amount. And that's how you pay back a bit in principal plus how much you owe them after 30 days. That's roughly the general gist of borrowing money, okay? So if you look at this formula, the compound interest, actually, we don't normally teach it to the general team, and we don't teach it to year 9 and 10, but that's your exponential model. If you realize P is the amount that you borrow, which is A naught. E, which is the base, well, 1 is how much you're starting off with. It's 100% of what you borrow plus the percentage that you increase it by. So obviously with interest rates, it goes up. Same thing if you invested into shares and you get certain dividends, that's the plus percentage. Obviously, if you're losing depreciation, so for example, you bought a car, you buy it now for, I don't know, 30,000, then obviously in the next 15 years, it's not going to be 30,000 anymore, and it's definitely not going to be 40,000. It's likely that it's dropped. That percentage that drops, that's where the sign changes. So it's either plus or minus, so growth or decay. And then N is the amount of times that they decay it. Do they decay it every day? Do they decay it every month, every year? And that's where the number of compounding comes in. So N is normally counted in years, but it depends on how many times do you increase or decrease the current value.
Given that the principal and the rate are 1, the more you compound the interest, like the more frequently you compound it, that equation is going to approach E, isn't it?
That I haven't thought about.
Isn't that like the most... When anyone asks what E is, that's what they always...
I think that's the idea. The idea is that it eventually approaches that point, but I'll need to think about that before I confirm that. Let me check that. Yep. So what you see here is essentially the exponential form that you've got a base. In our case, the compound formula was 1 plus the rate out of 100, and that is just your N, how many times you compound. The K is, if it's every day, then it's 365 days, because it's 365 times that's how many times in a year. So T is normally years, and then K is your dilation there. So what I'm trying to do there is trying to show you that depending on your question, you have to read, is it increasing or decreasing? That tells you if it's growth or decay, and that changes your base. It also changes your time. Okay? Now, to work it out, we'll just work out very simply here. K is the dilation, which we know. So obviously if it's positive, then it stays the same shape. It's exponential, so hence it's growth. But if it's negative, then it's a reflection in the y-axis, and the graph does not look exponential this way, but it looks this way. So hence it decays. So right here, this is decay when K is less than 0, meaning K is negative. And essentially I'm just saying you've got a reflection in the y-axis. Okay. Now, in your textbook, they give you this other formula, which really is still an exponential. This is still an exponential model, but I find that students get confused with the word generation time. So that's why I'm doing this example with you. This formula is exactly the same as what you see as a general exponential form. They still have the total amount at the end of a certain duration, the initial amount, okay, so N naught, is the initial number of cells. So this is specifically for cell growth problems. And 2, why is it 2? It's not always 2, but the problems that you get in your textbook will be 2. And the reason why is because they split in 2. So an example of a cell growth problem is something they're trying to say is you start off with 1 bacteria, and after a certain amount of minutes, so let's say every 2 minutes, it splits up into another 2. Then another 2 minutes, so let's say start at 0 time here, 2 minutes, and then at 4 minutes mark, this one splits up into 2, this one splits up into 2. And so what you can see is it follows an exponential model of base 2. Starts off with 1, so 2 to the power of 0 is 1, 2 to the power of 1 is 2, 2 to the power of 2 is 4. See that? So it's splitting up. So you can use a base 2, that's why it's always base 2 there, because they're saying it splits up into 2 for every minute. Now, the change is like not every bacteria splits up itself into every 2 minutes. It could be every minute. It could be every 5 minutes. And that's what they mean when they say generation time. Versus T. T is the total time. So let's say in 10 minutes. Okay, in 10 minutes, that could be T. But generation time, which they call TD, that's how often or how long it takes before it does actually split. If I told you it splits every 2 minutes, how many times would it had split in 10 minutes? 5. And logically what you would have done was you would have done total time divided by how many times they split. So 10 divided by 2 gives you 5, and that's why the formula, as you can see, it's total time, or whatever the actual time is, divided by the generation time. So if it's every minute, then you would have said it splits 10 times. If it was every 10 minutes, you would have said it splits only once. Does that make sense? Okay, so that's what the formula is. Nothing too crazy. It's just that when you read a problem without understanding that, you might be lost on what you need to do. So here, let's do a model from your example 32. What is the generation time? So they want to figure out how long does a cell will split itself into two, so it divides into two, right here. How long will it take for it to split into two? Okay, if you started off with 5,000, so a particular bacteria increases from 5,000 to 100,000. Okay, so in how long? In 4 hours. So we know that the total time is 4 hours. We know that you started off with 5,000 of these bacteria. And then after 4 hours, we know we end up with 100,000. So the question is, how long does this cell, this growth cell, take for it to split into two? Because clearly it's a base 2. Make sense? Oh. Again. All right, here we go. So 4 hours. One of the first things you should note is T. You can't do 10 minutes divided by 2 minutes if they're not the same units. If I said 10 hours divided by 2 minutes, that doesn't make sense, right? 10 divided by 2 is still 5. So you need to make sure the time is the same. So since we're asking for generation in minutes, so TD minutes, you need to make sure that this 4 hours is in minutes. Now, what's 4 hours in minutes? Let's go with Adrian. What's 4 hours in minutes? 240. So this should be 240 minutes. And what we're trying to figure out is TD. So if you were to calculate this now, you can use your CAS to do it, or you can do it, again, by hand. So let's do it. The final amount is 100,000 after 4 hours. 100,000 is equal to, you start off with 5,000 times base 2, because you're splitting up into 2 for every generation minute or minutes. And then the total number of minutes was 240 minutes divided by what we don't know, which is TD. This is what you're going to do. Now you can solve it by hand or solve by CAS. I'm going to do the hand method just to see if you know how to solve this. Let's go. What's the first thing you're going to do? BODMAS, going backwards is Sam Dobb. What are you going to get rid of? Good. The times 5,000, divide both sides by 5,000. So here we go. Divide both sides by 5,000. And what's 100,000 divided by 5,000? Take off the zeros. So 100 divided by 5 is 20. So you got 20 is equal to 2 to the power of 240 over TD. Now from this step, there's a lot of ways to do it. You guys have a calculator that can actually do the inverse of base 2. So you could do log base 2 if you wanted to. Or if you didn't, you could do log base E or log base 10. Your textbooks likely will stick to base 10 or base E. Okay, so if you look at the back and it looks a bit different than yours, it's only simply because in the past, we only did log base 10 and base E. Okay, you choose either way. So here, I'll stick to what the textbook might do. So from here, choose 10 or E. We'll just do E for the sake of it. So ln is nice and easy. So I'll do log base E. So ln is log base E, or I'll just write it out. Log base E of the left. Whatever you do to the left side, you do to the right. Now, obviously, log E and 2 aren't going to cancel out. So what are you going to do now? You end up with this step now. You got log E of 20 on the left. And you got log E of 2 to the power of 240 over TD. Log E and 2 aren't going to cancel out. So what do you do? Very good. This is log rule number 3. Very typical exam technique. Okay, so at the end of your exam, log rule number 3 is very key. You can bring the power down to isolate it away from the log. And that now gives you get, what's that? That's 240 over TD times log E of 2. And over here, you've got log E of 20. I know there's a bit of fractions and all that, but that's why the examiners like to do that in exam 1. So from here, how do I get TD? My goal is to get TD. I need to find what TD equals to. What do you do next? Yeah, let's get rid of that times. And I just think that getting rid of this is a good start. So let's divide both sides by log E of 2. So I divide this by log E of 2. I divide this by log E of 2. Log E of 2 divided by log E of 2 cancels out. And you're on to the next step. So now you've got log E of 20 divided by log E of 2 is equal to 240 over TD. Now, there's a lot of things that you can do from here to get TD. Depends on your algebra. What's the technique or what you're going to do next? A lot of people have different ideas at this point. And all of them can be correct. Yes, you can do that. Yeah. So essentially we are getting rid of 240. So if I divide times by 240 on this side, times this by 240 or 1 on 240, these two will cancel out. A tip that to simplify your life as well is you can't, because they're fractional, they're proportional at the moment. One tip is that if you do not like fractions and you need to solve TD on the bottom, you can actually do the reciprocal. Okay, you do 1 divided by the right-hand side and 1 divided by the left-hand side, and it flips the fraction. So by doing that, you can get TD over 240 is equal to log E2 over log E of 20. And the reason why I like to teach students that is that makes your life easier now. Whereas before, with Joe's technique, you still end up with the 1 on TD. And for some students, that could be a bit intimidating. Yeah? So now that if you did the reciprocal on both sides, which is possible, whatever you do to the left, you do to the right. As long as you do that, it's always equivalent. Now it's easier. Your goal is to find TD. That's divided by 240. So if you multiply both sides by 240, you will get your answer for the generation time. So here, TD is equal to 240 times log E of 2 all over log E of 20. Okay, now I know that you could have done it all on your CAS in the first step, but if it was exam 1, if they're looking for an exact answer, then that's what you would do. Another common mistake is that they will do log E of 2 divided by log E of 20. They think they mix it up with index laws, and then they'll subtract 2 from 20. Because of that, it would be wrong too. That's your final answer. Let's type it in our CAS. Let's see if we get the same answers, okay? So here we go. We should have 240 multiplied to ln, so control ln of 2 divided by ln of, what was it again? Whoops. What was the bottom one? 20. So this is what you should get. You should get 55.53. Or if you did it from the beginning, you could have done menu 3-1 solve. And what am I solving for? I'm solving for 100,000 equals 5,000 multiplied 2 to the power of 240 over x. Solve for x. And you get the same thing. Okay, so one was by hand. The other one you can do by CAS. Cool? So far so good. That's your textbook question. They likely would have gone through the algebra there. I do want you to practice the algebra as well, just so that you get familiar with whether it's log E or log base 2 to get rid of. You're going to be comfortable moving between them. Okay? Because that will help you with example 3. All right. Let's do a typical example now. So move over to the next page. Example 2. Example 2. Is there anyone who doesn't have a copy? No? Okay, cool. Example 2. Let's do this one. So, a population of 2,500 lizards increases by 30% after every 4 months. So think about that key part. Think about money and borrowing money from the bank. It's very similar. You borrow money from the bank, so say $1 million increases by, interest increases by 6.05, whatever it is, % per annum after every year. This is now after every 4 months. They want you to write a formula that gives the number of lizards after T years. What's confusing is that after 4 months. So I'm going to pause the video. I'm going to get you to think, what is the model? Because I gave you a general model. Here's the general model. So A, total amount is equal to your initial amount times your base to the power of KT. Can you try to model that example? I'll give you, let's say, 3 minutes. All right. First question. Is this a growth or a decay problem? Let's go with Samuel. Is this growth or decay? It's growth, clearly, because it says increases. So it should be growth. You expect that the number of lizards should be increasing, not decreasing, so it's growth. A0, well, we're clearly starting off with 2,500. Okay, now T. This is the part you have to think about. They wanted you to write a formula that gives the number of lizards after T years. All right, so after a certain amount of time, in 1 year, for hypothetically, every 4 months, it increases by 30%. Now, the first thing is you need to think about when we say increases by 30%, just like the compound formula, you have your starting amount, which is 2,500, which is 100% of itself, plus an extra 30%. So what you should have already is you should have started off with 2,500. So that's your principal. That's what you start off with, times 100% of itself plus an extra 30%, which is really the same thing as saying 1 plus 30 over 100, which is 1.3, by the way. The only problem we're missing now is this top bit. It's the time. Now, if you just put T, the problem is that it's not every year that it increases by 30%. It increases for every 4 months. So let's think about it logically. If it was in 1 year and every 4 months it increases by 30%, how many times does it increase by 30% in a year? 3. So that means that if T was 1, then it would have been times it by 3. So if you had to model this, if it was 2 years, it would have been 2 times the 3. It would have been 6 times, right? So how you would model it is you would say, well, it would be T years times 3 because it's every 4 months. If you really want to know the true formula for it, it's your generation time. It's that cell growth one. It would have been T divided by TD. So you think about it, TD is every 4 months. How many months in 1 year? 12. 12 divided by 4 gives you 3. That's how it ends up with 3T. True? Okay, so that's the logic to it. So here was the hardest part to understand. It's actually 3T. So up here, it should be compounded 3T. Or another way of thinking about it is your formula should have been 1.3, which is 30% every 4 months, means it's compounded in 1 year to the power 3. That's essentially what it is. Okay, then it's every 3T, and you start off with 2,500. That's essentially the idea. So that may be a bit hard for some students to understand, just that bit there. That's where the application comes in. All right, so to model, what is your formula? It should be 2,500 times 1.3 to the power of 3T. Hands up if you got that model. Hands up if you got at least 2,500 and the 1.3, you just messed up on the time. Okay, good. Very good. All right, so to answer the question in part B, how long will it take for the population to reach 1,500? Essentially, you're just saying A is equal to 1,500, and your goal is to solve this. 1,500 is equal to 2,500 times 1.3 to the power of 3T. Is it 15,000? Oh, 15,000. Thank you. 15,000. And you can, again, do this by hand, but by this point, I already did the hand method with you. From here, do it on your CAS. Go to your CAS calculator. Let's do menu 3.1. So menu 3.1, solve. 15,000 is equal to 2,500 times 1.3 to the power of 3 times x. Solve for x. 2.276, but what's the question ask you? They want it in to the nearest month. So in years and months. So right now, if I write down the answer, T is currently equal to 2.2764. 2764. This is years. How do I convert that to months? Because I clearly know it's 2 years already. What's the 0.2764 in months? How do you do that? Times 12. Because that's in years. So if you want to know how many months, times it by 12. So that 0.2764, 0.2764 roughly times 12 gives you 3.3. So what does that mean? Takes about 3 months and whatever 0.3 is. But because it says nearest month, 3.3 is closest to 3 months. So you say here that's 2 years and 3 months. Oh, I see what you're thinking. That's true. That's true. In this question, you're right, actually. Mathematically, it's closest to 2 years and 3 months. But logically and application-wise, because it's asking how long will it take the population to reach 15,000, they'll be short of 15,000. So the next closest month would have to be 4 months. You're right. So we need to round that up to 4. Mathematically, it should be closest to 3, but then 2 years, 2.3 would be too short. It won't actually make 15,000. So if you want to reach 15,000, at minimum, in terms of months, it would have to be 4 months. Good pickup. Thank you for correcting me on that one. That is true. All right. Your last example, I'm going to give you about 7 to 8 minutes because it might require a bit of thinking. So this one is challenging, especially the next two. The first one, if you play around with what the model's given to you, you should be able to nicely get K. Then B is pretty easy. Once you get K, B follows on, but C and D gets you to think a bit. Okay? I'm going to give you 7 to 8 minutes. I'm going to pause the recording. All right, let's go. I'm hearing a lot of correct answers. I'm sort of sitting here listening to you guys solve. First one, you've got a model, which is here. They say that when the intensity of light is it is halved when the diver is at 5 meters below the surface. So that's essentially telling you that D, when D equals to 5, then the intensity is equal to half its starting point. Oh. Okay, so when D equals 5, your intensity, the light intensity, is halved. Well, what is it halving? Well, it's halving what you started off with. So whatever you started off with is halved. So that's going to be the first key thing. So then the first part of the question, if your formula is I is equal to I naught e to the negative kd, well then when D equals to 5, then I has to equal to half of I naught. So if I do that, this is what I'm going to get in my next line. I get I naught, so half of I naught, because the I becomes half of I naught, is equal to I naught times e to the power of negative k times 5. You see that? I'm just substituting D. So D is 5. It's over there. And then this I, I'm substituting over here. Okay? And what's nice is that these kind of problems in your textbooks is that you can divide both sides by the initial amount and they cancel out nicely. Hands up if you got up to this step where it's half equals to e to the negative k or 5k. Negative 5k. Hands up if you got that step. Very good. That was key. Okay, so getting up to that point, now you can use a CAS or you can do it by hand. I'm just going to use a CAS because I'm a bit lazy right now. So I'm going to go menu 3-1, so solve half. So 1 on 2 is equal to, whoops. Make sure this is Euler's number, so use the E button and not the letter E. So e to the power of negative 5 times k, solve for k. And you should get 0.138629294, but it says correct to 4 decimal places. So just from this step, k is approximately equal to 0.13862944, but we're rounding it off to 4 decimal places, so it should be 0.1386. Hands up if you got K correct. Oh, good start. So then B was easy. B just says redefine the function. So on your CAS, you redefine it, and you just say I is equal to I naught e to the negative of 0.1386 times D. That's B. Now, part C, which was a very good discussion that you guys had over here. That's literally what the question was trying to get you to do. In part C, which is on the next page, but I'm going to just do it here, they said that D, depth is 10 meters. So when you're 10 meters below, how much light is available? So you start off with a certain amount, and the question is, what's the percentage of light available at that depth? So if you sub it in, I is equal to I naught e to the negative of 0.1386 times 10, because d is equal to 10. When you work out this value, which is this entire thing, e to the power of negative 0.1386 times 10, that will give you a value. But let's have a look at this value. So I'm going to go back here. I'm going to do e to the power of negative 0.1386 times 10. That gives you 0.2500736. So what this is saying is your intensity of light is equal to I naught times 0.25000736. That's already telling you a proportion of your intensity. At depth 10, you're getting about a quarter of the intensity. That's about 25%. If you change that to a percentage, that is the proportion of intensity left over. So your answer in terms of percentage should be approximately, does it say round off? To the nearest whole number. So this to the nearest whole number as a percentage is 25%. 25% of light. Hands up if you understood that question C. That was a bit trickier. Okay, good, because that's typical. Okay, they typically do that. So it's you're timesing it by a certain amount, times by 0.25 is essentially you're timesing it by 25%. Right? So then if you understood that, that links into part D. Boys, can you please not speak while I'm speaking? Part D, it's a similar idea, except this time you want the intensity of light to be less than 0.1, which is 10%. Okay, so what they're really saying there is before you had 25%, well, what if I want the intensity of light to be less than 10% of its intensity? So just in case you didn't understand, this was the little hint to give it to you. It says intensity of light is less than 0.1, which is 10% of I naught. And if you didn't get C, hopefully this part of D would also give you a hint to do C, because that's telling you 0.1 is essentially that 10%. Okay? So all you have to do in part D was actually to solve I less than 0.1 times I naught. But I naught, we already have the equation for I. And how do we then do this? Essentially, you are solving when is the intensity. So when's the intensity? And our intensity formula was I naught. What was it again? Times e to the power of negative, someone remind me? Okay, times by d, less than 0.1 times I naught. And remember, what are you trying to find in this question? They're asking you to find how deep. So you're essentially finding d. So if you look at this equation that I just wrote out, you want the intensity to be less than 10% of the original. And here's my intensity formula that we figured out. D is what we're trying to find. Again, you can type this in your CAS, or you can do it by hand, but notice that the I naughts will cancel out again. So here, I naughts dividing by I naught, divide by I naught, cancels out. So really all you have to work out on your CAS is e to the negative 0.31386 times d less than 0.1. And then from here you can do it on your CAS, or you can even graph it and do it. Yep. If artificial light is necessary when the intensity of light is less than 0.1 of the intensity at the surface, that is, I is less than 0.1 of I, find how deep a diver can go before the artificial light is necessary. Oh, yes, that's right. You let it equal to 0.1. My bad. Very good. And then you just solve for D from there. Okay, so do it in your CAS, and let's see. Solve e to the power of negative 0.1386 times d is equal to 0.1 comma d. Depth of 16 didn't want rounded to a certain value. 2 decimal places. Did I type it right too? Hands up if you got that question. Right, pretty cool. So that was a nice question. I thought it was nice to show you. So you can see the changes. This is a growth example. This is a typical exponential question. And then the bottom one is your intensity, light intensity, where you have to do a bit of modeling, problem solving. All right, team? So I'm going to stop the video there.